Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be doing Unit 12, Lesson number 2, on sets and probability. So this entire unit is on probability and the quantifying of chance, right? The quantifying of randomness, if you will, how likely something is to happen. And one of the major tools that we use when we do probability and think about probability is the idea of a set. So we're going to begin today by making sure we understand what a set is. Let's jump into that right away. All right, definition of a set. A set's not a tough thing, right? It's simply a collection of things. Numbers, objects, outcomes, etc., that satisfy a well-defined criteria. Now, the idea of a well-defined criteria is actually pretty important, right? The idea is, with a set, there's got to be something, some description of the elements in a set, the things that are in it, right? Where you can say, yeah, that thing's in it, or that thing's not in it, right? I mean, so if I say the set of all even numbers, there's no question about whether or not a given number is in that set. Is it divisible by 2 or not? Is 2 a factor of it, right? So that's where we have to have a well-defined criteria. It can't be wishy-washy, if you will. All right, so let's take a look at a problem involving sets. Exercise number 1 says the set A, oftentimes sets are represented by capital letters. The set A is defined as a collection of all integers that are greater than 0 and less than 10. So there's your well-defined criteria, right? It's got to be an integer, right? Which means it's a whole number, no fractions, nothing like that are greater than 0 and less than 10. Letter A says, write set A out in roster form. So sets, which we've written many times, can be written in many different ways, including interval notation and stuff like that. But this particular set can be written as a list. That's called roster form. Now I'm listing these in order, but they certainly wouldn't have to be listed in order. All right, sets aren't ordered, they're just collections. So there they are. There's set A in roster form. All right, set B, or letter B says show set A in Venn diagram form. This will be a very simple Venn diagram. So a Venn diagram is typically a circle or multiple circles that show the elements of a set. So when I say this is going to be a simple Venn diagram, I mean this is going to be a simple Venn diagram. There it is, right? That's set A. All right. Now letter C introduces a new piece of terminology. A subset is any set whose elements are all contained within another set. Give 2 possible rules that could define subsets of A, and then write the sets as B and C in roster form. Do sets B and C have any elements in common? All right, so this one is really kind of quite an ambiguous question, all right, because we're going to create 2 more sets that are subsets of A, all right. Now, because they're sets, they have to have well-defined criteria, all right. Now, again, we could have all sorts of things, but here's one that would be pretty common. Set B's definition, all elements of A that are even. Sorry about that, ran out of room. And that's not the word even. There's, it's like once I make the spelling mistake, it just gets worse and worse. Let's try that again. All elements of set A that are even. That's a well-defined criteria, right? Because 1's not even, but 2 is. 3 is not even, but 4 is, etc. Right? That is then B is a subset of A because all the elements of B are in A. Now, of course, I could say set C's definition is all elements that are odd. That'd be fine, but I kind of want to have 2 subsets that overlap, that have elements in common. So let's say all elements of A that are multiples of 3. All right, we should know what multiples are. right? That's again very well-defined criteria. So 3 times 1 is a multiple of 3. 3 times 2 is a multiple of 3. 3 times 3 is a multiple of 3. Right? 3, 6, 9, multiples of 3 all lie within A. And yeah, they do have elements in common, right? The one element they have in common, known as their intersection, and we'll work more with intersections. Intersection, right? Where those two, if you will, cross. And we'll work more with intersections in a future lesson, so no need to know that terminology right now. But where two sets, or the elements that two sets have in common, right, there is just the element 6. All right, so lots of different terminology in this problem. Nothing with probability yet, okay? So pause the video now, write down anything you need to. All right, let's clear this out and keep working with sets. Maybe bring some probability in. Exercise 2. Consider an experiment where we first toss a coin and note the outcome, and then roll a 6-sided die and note the outcome. This is what's known as a multi-stage event. Multi-stage event, because more than one thing is happening. We're both tossing a coin and we're rolling a die. Letter A says write out a set of ordered pairs, such as 8, 4, that represents all outcomes for this experiment. Okay, so in other words, we want a set where the elements, well-defined criteria, are the outcomes to this experiment. And we're going to call this S, the sample space. So one outcome to this experiment is that we got an H on the coin and we got a 1 on the die. Right? That's one outcome. We could, of course, write that as 1, H, but we're just choosing to put the outcome of the coin first. Then, of course, we could get a head and a 2, etc. Why don't you pause the video now and write out the rest of the elements of this set. All right. It's pretty easy, right? We could get a head and then a 3. We could get a head and a 4. We could get a head and a 5. And we could get a head and a 6. Then, of course, we could get a tail and a 1. We could get a tail and a 2. A tail and a 3. And that's it. Now remember, a set is just a collection of things, and those things are these ordered pairs, and those ordered pairs are simply the outcome on the coin along with the outcome on the die. All right. Letter B says, write a set of ordered pairs that represents the event of getting a tail and getting an even number. Call this set A. So now set A is a subset of set S, right? So set A is another collection of stuff, right? Collection of things, all right? But these things are all the elements in here where we got a head, no, I'm sorry, we got a tail, and we got an even. Pause the video now and write all of those out. All right, let's go through it. Well, we got to have a tail, so a tail and 2, a tail and 4, and a tail and 6, right? And obviously you can see those here. Here's those elements, right? And they just became elements of A. Now letter C introduces us to another piece of terminology that's important with sets. The complement of a set, all right? The complement of a set will be all the events in the sample space, in S, that do not belong to set A. So sometimes we'll call that the complement not A, right? It's a good way to call it. In this, we're actually going to call it set B, but sometimes they call it not A. Sometimes they'll have like a little funny sign here. Sometimes they'll have a little funny sign here. Since we're not really sure what any standardized test is going to do, we'll just call it the complement of set A. Now, we want to write it out. Well, the complement of set A is everything in the sample space that's not an A. Well, this is going to take a little bit to write out because that includes all the ones with heads, right? Head 1, head 2, head 3, head 4, or 4 head 5, head 6, a little math humor there, not very good math humor, tail 1, tail 2, oh no, that one was in A, tail 3, and tail 5. All right, that's it. That's the complement of A. And finally, letter D says find the probability of A and the probability of B. So let's remind you about the fundamental definition of probability. And now we can really kind of understand this like little n a little bit more. NA is just the number of elements in set A. All right? And of course, that's 3. And NS is the number of elements in set S, which was what? 1, 2, 3, 4, 5, 6. It was 12. So the probability of event A is 1/4, or 0.25, or 25%. Now the probability of B, well, that's going to be the number of elements in B divided by the number of elements in the sample space, and that's going to be 9 elements in B. Right? There's 9 of those. Out of 12, that would reduce down to 3/4. Or if you like it as a decimal, 0.75, or if you like it as a percent, 75%. All right? So again, we want to have a really good grasp of both what a set is, what a well-defined criteria for the set is, how we can list the elements of a set, if we can at all. There's some sets where there's so many elements you either can't list them or listing them is just, not practical. And then we want to understand that in terms of calculating probabilities. But it's pretty easy. All right, so pause the video now, write down anything you need to. Okay, whoops, let's clear out the text. All right. Exercise 3. Consider rolling a single 6-sided die and recording the result. All right, simple enough. Let A be the event of rolling a number greater than 4, and let B be the complement of set A. Draw a Venn diagram that illustrates the sample set space S and sets A and B. All right, so now it's a little bit more complex. All right, here we go. Actually, let me clear this for a second. Very often with the sample space in a Venn diagram, they draw that with a rectangle. All right, and then very often a little s will be put right here. Now, what do we got? Well, in set A in S in general, right? We're rolling a standard 6-sided die, so we're going to put the numbers 1 through 6 in here. All right, but the only ones that are going to go in A is the event of rolling a number greater than 4, will be 5 and 6. So that's set A, right? Set B is its complement. So it's got to contain everything else that's in the sample space. So there's no numbers hanging out here, right? There's no numbers that are in A that aren't in B, right? Sorry, there's no numbers that are not in either A or B hanging out here. Now, letter B, this is simple enough, says find the probability of A, find the probability of B. Pause the video really quick and write these down. All right, well, this is simple, right? The probability of A, I'm going to keep emphasizing this formula. I know that you probably didn't write it down, and that's quite all right, right? The probability of A is 2/6. Now, I can reduce that down to 1/3, but I actually kind of like it as 2/6. The probability of B, easy enough, the number of elements in B divided by the number of elements in the set. There are 4 elements in B, there are 6 elements overall. We can write it like that, or we could reduce it to 2/3, either way. Now letter C says, what is true about the sum P of A plus B of B? P of B. Go ahead and figure that out. Use either the reduced forms or the unreduced forms. Well, what you should have found out was that P of A plus P of B, which will be 2/6 plus 4/6. Oh, well, we have a common denominator, which is 6/6 is 1. All right? 1, or 100%, right? Now, letter D says, prove that the sum of the probability of an event with the probability of its complement will always be 1. So, whenever you add the probability of an event with the probability of its complement, you will always get 1. All right? Now, how would you go about proving that? How would you go about explaining that? Pause the video now and think about this sum. All right, let's go through it. There's definitely a sort of dry way of doing this, and let's take a look at it. We're going to add the probability of A with the probability of not A. All right, well, that's going to be the number of elements in A divided by the number of elements in the sample space plus the number of elements not in A divided by the number of elements in the sample set. Well, the real question is, how do you know how many things are in not A? How do you know? Well, the number of elements that are not in A will be the number of elements in the sample set minus the number of elements in A. So all of this will be the number of elements in A divided by the number of elements in the sample set plus the number of elements in the sample set minus the number of elements in A, all divided by the number of elements in the sample set. Because these fractions have a common denominator, I can now add them together, and I'll get NA plus NS minus, running out of room, minus NA divided by NS. Sorry about that, but do you notice that these two are opposites, right? Positive NA, negative NA. So they cancel. What do we get? We get the number of elements in the sample space divided by the number of elements in the sample space, and that has to be 1. Now, there's a lot of different ways, though, that you can kind of get a grasp for that, and almost everybody understands this. I mean, if you've got, an event happening and then an event not happening, the probability that it happens plus the probability that it doesn't happen has to be 100%, because there's really no in-between if you have well-defined criteria. Again, if you got kind of wishy-washy criteria, then, maybe there is something in between. But if the event is it rains and the complement is it doesn't rain, then the probability it rains plus the probability it doesn't rain has to add up to 100%. It has to. All right, pause the video now and write down anything you need to. Okay, zap this stuff. All right, now that idea that the probability of an event plus the probability of its complement equals 100%, or 1, is something that we use all the time. So let's take a look at that in exercise 4. It says answer each of the following problems by using the relationship developed in exercise 3D. In other words, the probability of an event plus the probability of its complement is equal to 1. So letter A says, if the probability I draw a red marble from a bag is 3/17, what is the probability that I won't draw a red marble from a bag, right? Well, again, the probability of red plus the probability of not red must be equal to 1. All right, well, the probability of red was 3/17 plus the probability of not red must be equal to 1. So we subtract 3/17 from both sides, and the probability that we're not red is 17/17 minus 3/17 gives me 14/17. Now again, I bet a lot of people wouldn't even do that. I bet a lot of people would say, well, the probability that I draw a red marble is 3 out of 17. The probability I don't draw a red marble must be 14 out of 17, right? And that makes a lot of sense from the perspective of, yeah, let's say I got 17 marbles and 3 of them are red. Well, 14 of them are not red. And it certainly works out that way just fine, right? So if you've got that intuition, use it. Use it. All right, letter B. If the probability it will rain tomorrow is 20%, what is the probability it won't rain tomorrow? Well, again, kind of going through this amazingly easy idea, the probability it'll rain plus probability it won't rain must be 100%. It's got to be. So if the probability that will rain is 20%, then the probability it does not rain must be 80%. Okay? So we use this idea all the time. We'll use it in a more sophisticated way later on in this unit when it is easier to calculate the probability of a complement and then just subtract it from 1 or 100% if you're using percents to figure out the complement of the event that you care about. We'll see that a little bit later on. Pause the video now, write down anything you need to. All right, clear this out. Let's take a look at one more problem. Exercise number 5. 2 four-sided die are rolled and the number on each is noted. So this is again another example of what we call a multi-stage experiment because 2 things are happening. We're rolling a die and we're rolling another die. All right, now this is going to be a little bit weird because they're four-sided die, okay? They're what are called tetrahedron. Letter A says, draw a tree diagram that represents all outcomes in the sample space. How many are there? Now I know tree diagrams are relatively new in terms of review for you, but remember it's very simple. This is just a way to keep track of what happens, right? It's this idea of, look, if I roll the first die, I could get a 1, I could get a 2, I could get a 3, I could get a 4. So this is just what I roll on the first die. This is just helping me keep track of what's happening. Then, given that I rolled a 1 on the first die, I could, of course, on the second die, roll a 1, a 2, a 3, or a 4. On the second die, I could roll a 1, a 2, a 3, or a 4. On the third die, a 1, a 2, a 3, or a 4. 1, 2, 3, 4. Now again, the idea would be, let me just use some red. If I traced this path, okay, what that is one particular outcome, that path, and that's the outcome of rolling a 2 on the first die and a 3 on the second die. Now, that's actually different from this path, where I rolled a 3 on the first die and a 2 on the second die. Now, you might think to yourself, yeah, but ultimately you rolled a 3 and a 2, okay? But they are 2 different things happening. They're 2 different things. Imagine like one of the die is colored blue and one of the die is colored green, right? This represents 2 different things, even though you might think of them as the same event, right? They're not the same outcome. And they might fall into the same event, i.e. rolling a 3 and a 2, but they're not the same outcome. Now the question is, how many outcomes are there? How many outcomes are there? Think about that while I erase and turn back to blue. Well, there are 16, right? And again, you can count them by just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You can count them by counting how many terminal branches there are. Now, letter B says, what is the probability that you don't get 2 of the same number? That you don't get 2 of the same number. All right. Well, we could list our sample space. We really have our sample space sitting here. But let's think about the probability that we get 2 of the same number, right? What is that? Well, that would be a 1, 1, a 2, 2, a 3, 3, and a 4, 4. So that would be 4 out of those 16. So the probability we don't get the same number don't get the same number will have to be 1 minus the probability that we do get the same number. So that'll be 1 minus 4/16, and that will be 12/16. It's okay to leave it like that. That's also equal to 3/4, or 0.75, or 75%. Lots of different ways to leave that answer. All right, so a little more practice with tree diagrams, a little more practice with the idea of complements and sets. Pause the video now and write down anything you need to. Okay, let's get rid of this and finish up. So, because of the fundamental definition of probability, i.e., the probability of an event can be thought of as figuring out how many outcomes fall into the event and dividing by the number of outcomes that are in the sample space. Because of that, we need to have a firm feeling for what a set is. What a set is, what a well-defined criteria is, what an outcome is, what an element of a set is, what the complement of a set is, right? So make sure that you're working with all this terminology and understanding it as much as you can throughout these lessons and throughout this unit. All right, I'd like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.